And today we continue discussing of the description of local type Gaussian random process via expansion of it onto the series of orthogonal polynomials. Last time we began to consider the following examples. We considered one-dimensional linear process and discussed its local time at some point y. We already agreed to denote such objects by the formal expression concentrated magnitude of 1 dt. And our aim is to expand it in a series from k equals 0 to 50. And here we must have orthogonal infinite dimensional orthogonal polynomials, which from the Wiener process. And last time we agreed that such orthogonal polynomials have a following kind. I will explain what is theta k. A k P1 P D T. Here delta k was a simplex where coordinates are ordered in non-decreasing order. And AK is square integrate function there. So AK belongs to P2 and power. It was mentioned that this is excuse me, not T, but W1, W. Here, this expression was taken due to the formal reason. That now this multiple stochastic integral is properly defined. We just integrate first with respect to WT1, then WT2, and so on. And due to such order of the coordinates, this integral is properly defined. Moreover, if one take the expectation of delta k ak p1 pk dw p1 dw tk square, then this expectation will be equal to integral with respect to delta k ak p1 pk dt. So you see that it is a very convenient relationship. and summands in the series are also observed. But we define this thing properly, connecting it to the following formal expression. Sometimes it is useful to use such expression, the integral which respect not to simplex, but which respect to cube. And here is k, t1, tk, dw, t1, dwt. Of course, here we have not good order between coordinates, so this is just formal expression, and we decided last time for symmetric function ak to say that it is equal to k factorial multiplied on the integral with respect to simplex or the same. So here is just definition for symmetric function. It is equal to k factorial the integrals with respect to simplex. From this point of view, sometimes it is much easier to speak about such summands in the orthogonal expansion of the random variable. Now let's go to the problem how to find the elements of the orthogonal summand, orthogonal expansion for our local. To do this, we will proceed formally, and what we need, maybe we need to understand what is this. What is its orthogonal? Its orthogonal expansion. We already have one. Yes, let's use it. So we know that formally I emphasize that this is not random, but formally we have some series, say from k equal 0 to infinity. Here we got the following coefficient: 1 over k factorial, 1 over square root e minus y square d, and here is multiplied on hk from y over square root of t multiplied by t in k over 2 and multiplied by hk wt square root of t. Okay. So what I'm doing here? Last time we got the expression for delta, and here I can put W1 or another Gaussian regular sign, which is 0, 1 standard distribution. But now we have this one. We have this one. So one can, what one can do? Just put square root here, subtract it from the delta function using change of variant formulas, and then we will get expression like this. After we do this, one can check that this these three multipliers, when united together, gives us exactly integral with respect to the simplex from the Wiener process. So I insist that we can express the integral with respect to simplex of the Wiener process using Hermite polynomials. In order to do this, let us stop for a moment these calculations and check what expression has multiple integral from Wiener process with the trivial kernel. So now I am going to have an expression for such integrals. dk, dwt1, dwt. Moreover, I will put here t, which means that we have not a simplex up to the number 1, but we have simplex up to the number 2. Up to the number 2. So this is our and here to get the expression for this multiple integral, we will use a very good trick based on the so-called stochastic exponent. To do this, let us consider maybe simplest stochastic differential equation xt dwt starting from the point 1. So I am considering Cauchy problem for such very simple stochastic differential equation. For people who are not familiar even with stochastic differential equation, there are no any troubles in considering of such equation, because you see that it is a very familiar equation where we have here dt instead of wt. And what I will use to solve this equation, I just will use iteration method. So I will just just apply the iteration method, and then I can say that our solution x is equal to the sum from k equal 0 to infinity, and here is exactly the integral with respect to k2 dwt1 dwt. This is for once. Of course, we have usual agreement that when k is equal to 0, then our integral is equal to 1, our initial condition. Exactly as in the deterministic case, we have a very similar expansion for the usual exponent. And word exponent is important here, because now solution also can be expressed as an exponent, and we can have a right form, precise form of the solution as here. It is equal to the exponent of wt minus t over 2. Here we have the difference with the usual exponent, with the deterministic case, but one can see that this is exactly the solution using Ito formula for stochastic integral with respect to Wiener process. I am not going to do this because this is not the aim of our lectures. You can just trust in this formula or check if a formula in textbook and then check that it is exactly the solution for our question. But when we have such a formula, let me slightly rewrite it, because here is something interesting. You remember the definition of hk of x. Hk of x is equal to minus 1 k power e x squared divided by 2. Here dx, differential operator, is power k, applied to the function e minus x. From this point of view, one can check that the following formula holds. I even will write this formula using a rest. So if I put there, then it is equal to the following thing. It is equal to the following thing. Then I can say that I can apply now Taylor formula to this function because I know its derivatives. Yes, I know its derivatives. So if I am right, e minus x minus y squared divided by 2, then I can expand it with respect to y. I will get the following relationship. It's equal to the sum from k equals 0 to 50. Here is 1 over k factorial. Here is minus 1 in k power, y in k power, and here is dx k times e minus x squared. Yes. From this, I can check, substituting now this expression in this form. I can check that the following relation here is x squared over 2. That the following relation holds. E minus x squared multiplied by e xy minus y squared. I just open brackets here is equal to here we have this multipliers again, so I put it there. X over 2 multiplying the sum from k equal 0 to infinity. And then what we will see. Here is this one I substituted by hkx, hk of x divided by k factorial, and here is y in k power. So now let us cut these two things, and finally from this expression for Hermite polynomials we got the exponential generated function for these polynomials, namely e xy minus y squared over 2 will be equal to sum from k equals 0 to 50, hk x k factorial y. Now let us write again formula for our solution. E wt minus t over 2. Yes. So it can be expressed as follows: E wt over square root of t multiplied by square root of t minus square root of t square over 2. So one can conclude that our solution can be expressed as a sum from k equals 0 to 50. Here we have hk from wt over square root of t divided by k factorial and multiplied by t over k over 2. Yes. From other side, we have another expression to our solution. Just recall we applied successful approximation method and get the following: the same solution E wt minus t over 2 is equal to the sum of the multiple interval integrals. Here we have integral with respect to simplex theta kt, dwt1, dwtk. Now let us combine these summas. Of course, just from the formal equality of these two series, it does not follow that we have the equality of summas. But maybe you understand very easy that I can consider equation with lambda. So equation of the kind ex equal lambda x dw, and then put this lambda there, put it here, and get the expression with lambda and compare summas. So this is just a simple technical exercise, and doing it, one can check that we have very good formula, which will be very useful for us. Namely, we have the expression delta k or delta k tw t1 dw tk as a harmonic polynomial with some multipliers t k 2 k factorial hk wt square root of t. Now let's come back to our considerations. You remember that we have a formal expression. We have a formal expression for the delta y from wt. This is just square root. I have to put here square root. Let me do it. Dy wt square root of t. And now I am doing change of variance formula. Since I divided it here, I must do it do the same here, square root of t. Then I can continue because we already have an expression. This is square root of t, and here for this we have a right expression. It will be like the sum from k equal 1 and 0 to infinity. Here 1 over k factorial 1 square root of 2 pi. I use just 2 pi because this Gaussian is a standard one. Here is e minus y square over 2. And then we multiply by hk here w t excuse me, here firstly y, then multiply by hk wt square root of t. That's all. And now what I'm going to do, I just want to put the square root of t here, and I want to make the change of variables formula, because how do we get this? We apply our vector function to the product of the density on Hermite polynomials. Now I want to go back with the change of variable. Then we will see that I can put it here and here. So finally, I can have the following. I can have the following. It is equal to the sum k is equal to infinity. Here 1 over k factorial. Just combine with this one. hk wt over square root of t. To get the Wiener integral, I need such multiplier. I haven't it, so I will multiply it with t minus k over 2, and here is 1 square root of 2 minus 2. Here is hk y. We will put it there, and then it's equal to the sum from k equal 1 to infinity. Here what we will have? We will have the multiple Wiener integral. The integral with respect to delta kt, here dwt1, dw k multiply by now let's try to make some transformation of this expression. You know, okay, let's read it. T minus k square. Here is maybe even in this way, plus 1 plus 2, k plus 2, yes. Here is p1 from y, hk from y. So And now let us see what happened. We have already formal expression for the following. It is delta y wt. It's equal to this one. Now let's integrate it from 0 to 1 dt. From 0 to 1 dt. Yes, dt. Then what we will have? We will have the following. It will go out, just forget about it, but this will go inside of the stochastic integral. That means, let me write, it is equal sum from k equals 0 to 50, p1 y hk y z multiplied by the integral. I will put here the multi-integral 0 with respect to simplex delta k, but inside of delta k, I will have the following. I will have the integral with respect to this function. Yeah. So here will be the integral t integral from t k to 1. Here is t over minus k plus 2 over 2 dt dw p1 dw. Oh, that's okay. So now you can see, and one can check that this integral is properly defined. You can calculate it using estimation on hk, which you can estimation on hk that it grows at most as a square root of k factorial. One can check that the series converge. So now we can have an instrument to discuss at least local time for linear process, and one can do exactly the same for more complicated things related to general Gaussian processes, such as not only local time, but local time of self-intersection, and so on. But after this exam, we realized some problem. You see, here we have such a function in the negative power, and such kernel must be integrated in square with respect to our simplex. Where this function arises and what is it? How one can manage this problem? For example, for general process. So now let us discuss the condition when the local time will exist for general process. So let us consider now the process psi of t belongs to interval 0, 1, and I want to consider central case, so I will suppose xit is equal to 0. And I want to discuss the existence of the integral 0 to 1 delta y psi we already know this density of excitation measure if such measure exists, but still it is unclear when we can say that this formal expression has right meaning. Let us discuss the case when y equal to 0. It is just simplification of the formulas. So I will discuss such a case when y equal to 0. And then let me consider approximations which we already discussed. So we want to have some sequence h epsilon which tends to delta 0. This is a sequence of usual functions which goes to this generalized function delta 0 epsilon 0. And then we want to have the limit of such expression 0 to 1 h epsilon of psi of t dt. What we can do? Let us try to calculate. Let us try to calculate the expectation and the expectation of the square. If we will check that all these expressions have a limit, then one can conclude that these random variables also converge in square mean. To be more precise, we of course have to consider the product of two such expressions for different epsilon, but for simplicity, I will consider such case. So let's start from the expectation. We already have seen that this is more or less easy, and if I denote by sigma square of t the variance of psi t, then one can check that formally the expectation of integral from 0 to 1 delta 0 of psi of t is equal to integral from 0 to 1 p sigma squared t from 0 dt. Here is the density of Gaussian random variable with such variance. So it's equal to the integral from 0 to 1 1 square root of 2p sigma square of t dt. And if psi is not generated continuous in square mean Gaussian process, this variance also will be positive continuous function on the bounded interval, so it will be separated from 0, and this expression is final. So for the first moment, we actually don't need very deep and special investigation. It's not true for the second moment. Let us understand why it is not so easy. To do this, I will find special functions h epsilon. which approximate beta function. You remember, I need such a sequence which goes to beta function when epsilon tends to 0. But here it will be useful for me, more convenient for me, not to work with the choice like this one. H epsilon is indicator of 1 over 2 epsilon, indicator minus epsilon 6. Because of for calculations, it's easy to have such choice. H epsilon is equal to P epsilon. Again, Gaussian density, but with the variance epsilon and 0 mean. So from x, it is equal to 1 square root of 2 pi epsilon e minus x square divided by 2 epsilon. Here is the density. And then it's easy to check that this relation holds for such set of functions. When epsilon tends to 0. When variance tends to 0, Gaussian distribution becomes to be concentrated in the point 0. Now it's more convenient to calculate this expression like expectation of integral from 0 to 1 h epsilon from psi t dt square, it will be equal to integral from 0 to 1 h epsilon psi of t1 h epsilon psi of t2. Here is dt1 dt. In order to have the expression for this expectation, let us calculate separately the expectation of this function which is under integral. So we have to calculate the expectation of h of epsilon psi t1 h epsilon psi t2. It's equal to integral, double integral with respect to r. Here, h of epsilon of x, h of epsilon of y, and here is q t1 t2 xy dx dy. Here, what I am supposed that for t1, which is not equal to t2, the covariance matrix of our process, covariance ct1 psi t2 is strongly positive. So after we have such a function, it has a density qt1 t2, which I put there. What else we have to say? That I am considering such a case t1 is not equal to t2 because in the expression for mathematical expectation of the integral, square, we have such situation everywhere except diagonal, but diagonal is the Lebesgue measure, is of the Lebesgue measure 0. So I'm considering such an expression. Now let us for a moment go informally to the limit. Okay. We can have some reasons to go formally to the limit. Why? Because this can be rewritten. This can be rewritten, and it can be rewritten as follows. It is equal 1 over 2 pi. Here we have 1 and square root of the determinant. Here I will write C T1 T2 plus epsilon E. When we can just C T1 T2 C T1 T2 is the covariance matrix of psi T1 T2. Namely, it is expectation psi T1 square, expectation psi T1 psi T2, expectation psi T1 psi T2, expectation of psi T2 squared. Yes. Then Q is the Gaussian density related to this matrix. But this product is also Gaussian density. Why? Because it is a product of one-dimensional Gaussian densities with 0 mu and variance epsilon. So this is a Gaussian density with such covariance matrix and 0 mu. And here we have a convolution at the point 0, because we integrate with respect dx and dy. So we have just the expression for the convolution at the point 0. But what is the convolution of two Gaussian densities? By the fundamental property of Gaussian random vectors or Gaussian waves, it is again a density of the sum of independent Gaussian vectors with such and such densities. But when we sum independent Gaussian vectors, their covariance matrix add. So we have exactly such expression as this. Okay, now see what happens. We get the determinant of the positive matrix plus epsilon. Yeah? What we know? We know that when epsilon goes to 0, what we have? CT1, T2 plus epsilon 1 E is less than C T1, T2 plus epsilon 2 E when epsilon 1 is less than epsilon 2. Yes? Since then, this determinant is increasing function when epsilon tends to 0. Increase when epsilon tends to 0. So when we want to have a limit in the integral, and we want when we want to have some mathematical arguments to go to the to have a right to pass to the limit, we can apply just Lebesgue theorem about the monotone convergence. From this point of view, it is enough to us to understand that such an integral without any epsilon converges dt1 dt2. This is a main expression which we need to investigate. And of course, it is easy to understand that it is in any case, does it exist or not, does it define or not, we have such a formula that it is equal to two integrals with respect to simplex theta 2, and here is dt1, dt2, and then again square root of this determinant c t1 t2. And what we need the convergence of this integral to have a local time at point 0. And then we can investigate this determinant to have the sufficient condition to have local time. Because now T1 is less than D2. Then see what we have here. This determinant of the covariance matrix of psi T1, psi T2 is exactly equal to the variance of psi T1 multiplied with the conditional covariance. Multiply the conditional covariance of psi T2 with respect to psi T1. Please check this. This is very easy to use Gaussianity of this to joint Gaussianity of these random values. But when we have such a formula, it's also easy to see that it is less than greater or equal to variance of psi T1 multiplied by the variance of psi T2, not with respect to T1, but with respect to all the past of the process psi. Then what we have here, maybe it's better for me to write it there, multiply on the conditional covariance of psi T1 with respect to the all the past of our process psi up to the T1. Yes. Now let us remember that we already suppose that our process is not degenerated. So it is continuous square mean, and its variance is not equal to 0 at any point. Since then, one can check that this is greater than some constant. So what we conclude, that the sufficient condition for our Gaussian process to have local time is that the integral from 0 to 1 from integral excuse me yes, from 0 to 1 integral from T1 up to 1. Here we have dt1, dt2, and here we have square root of conditional variance of psi t2 with respect to all the past ft1 psi is less than. Here is the sufficient condition for existence of the local time for our Gaussian process. So S square limit in the square mean. So there exists only two limit, and epsilon tends to 0, integral from 0 to 1 h epsilon from psi t dt, and it is denoted by us integral different function at point 0 psi t dt. So what we need to control this one. And it was Simeon Berman who created such a well-known condition now as a Berman non-determinism. His condition consisted exactly in the controlling of this guy. So suppose that this is Berman non-determinism. Also called local non-determinism, sometimes called local. I will explain why. A local non-determinism condition. It looks like that that conditional variables of psi t2 under all the paths f t psi is greater or equal than some function phi t2 minus 1, where phi is non-decreasing and is such that integral from 0 to 1 ds phi s now have this lesson. Of course, it is. So you see, simply Berman proposed to control this conditional variance in order to get the local time. Now we understand several things. Now we understand that we can have good sufficient condition to have local times. We understand that the local time is the density of visitation measure. We understand that the local time can be expressed as a sum of orthogonal e-to-Wiener integrals, and we know how to get the summons of this expression. Also, we know that existence of the non-trivial positive local time at the point leads to the conclusion that the process of the field hits. So next lecture, it will be our concluding lecture. We will have the conditions and we will conditions to existence of the local time, and we will consider the sets of the visits of one point or sets of points of self-intersection, and discuss it fractal dimension, fractal measure, because we are expecting that our sets, when we visit some point, or our sets of parameters when we have the self-intersection or intersection between two different random processes, have complicated structure. So we will discuss Hausdorff dimension and Hausdorff measure of such sets. Today we finish our job. Thank you for attention. Maybe somebody has questions, please. Okay. If there are no questions, then see you at Wednesday.